Hello and welcome to today's lecture on minimizing switched capacitance. We have started our discussion on various techniques for minimizing switched capacitance, and in the last lecture I have discussed about hardware software trade-off, and we have seen some functionalities can be realized by software, and by doing so you can minimize the switch capacitance. And we have illustrated that with the help of two examples, AD converter and realization of processor architecture by using VLIW instead of superscalar. Okay. Today we shall focus on bus encoding, and this is the agenda of today's lecture. First I shall introduce basic concepts of bus encoding. After that I shall discuss several popular encoding techniques like gray encoding, gray coding, one-hot encoding, bus invert encoding and T0 encoding. So, these are some of the popular encoding techniques commonly used for minimizing switched capacitance. But before that, let me consider very basic concepts of bus encoding. Encoding is not a very new concept. It is being used for a long time, particularly in communication. In communication, we have seen it is used for various purposes. For example, one approach or one goal of coding is remove undesired correlation among information bits. So, you are sending information bits sequentially one after the other. So, whenever you are doing so, if you want to remove correlation, then you can do some kind of encoding, and then correlation between among various adjacent codes which are sent one after the other is removed. In fact, this is used while used in encryption, because whenever you are sending encrypted data, the other side or rather who are monitoring the bus or monitoring the communication medium should not be able to identify what is being sent. So, correlation among the data is removed, and correlation, by doing so, you cannot identify that this can be a particular bit pattern, particular information. So, this is used in encryption, and another type of encoding is used where coding is used to introduce controlled correlation. That means, you are sending consecutive data where you are introducing controlled correlation for various purposes. One purpose could be spectral shaping. For example, you are sending some data through a communication medium, and whenever you are sending that, then you have to do the spectral shaping such that the signal can be communicated with minimum attenuation. So, that means, the bandwidth of the medium is matched by spectral shaping, of the signal. This is one technique. Then timing recovery, sometimes it is used for the purpose of timing recovery. For example, you are familiar with local area networks. In Ethernet, Manchester encoding is done where where it is primarily used for the purpose of timing recovery. And then sometimes it is used for error detections. You are all familiar with the use of additional bits like parity, then cyclic redundancy code, and by doing that you can detect error as sometimes correct error. So, you can see these are being done by introducing controlled correlation among the data that is being sent. And in fact, as we shall see, the coding that we shall be doing, coding for reducing switching activity falls under the second category. That means, we shall be introducing controlled correlation whenever we shall be sending data such that the switch capacitance is minimized. That is the basic idea. Now, this will, by introducing sample to sample correlation such that the total number of bit transitions is reduced. So, this is the basic idea behind this bus encoding for low power. And whenever you will be communicating data bits in an appropriately coded form, that will reduce the switching activity. That means, the switching activity can be significantly reduced by doing that. Now, let us consider what do we really mean by bus encoding. You are having a one particular say sender, let us call me sender chip. Sender, right, it can be a chip, it can be a device, it can be a microprocessor, it can be a microcontroller, and you have got another chip, let it be called receiver. And you know the signal is going out of this chip and that is being sent to the receiver. So, whenever you are doing so, it has been found that the capacitance outside the chip, that is called at off chip capacitance, off chip capacitance has been found to be very high. Why it is high? We know that internal to the chip, various nodes have capacitance of the order of femtofarad. But whenever you take it outside the chip with the help of bonding wiring, padding and so on, take it to the pin, then the capacitance becomes of the order of picofarad. So, you can see it increases significant, several orders of magnitude higher, and obviously as you know the dynamic power dissipation is proportional to CL, and as the capacitance is very large, you have to minimize switching activity. So, switching activity has to be minimized, so that the dynamic power dissipation is reduced. Now, in this particular case, how you will be doing it? You will be in the sender, will be doing the encoding before sending, that will become part of it. So, here you will do encoding, and then after it is sent, after it is received by the receiver, it will do decoding to get back the data. Now, when the sender is sending, then it may be sending say from this side n bits, and the decoder may convert it to m bits, and then the encoder may convert it to m bits, and the decoder on the other side again it will convert it to n bits. Now, based on this, the encoding technique can be categorized into a number of types. For example, there are two possibilities. It can be a redundant encoding, in which case m is greater than n. That means, the number of bits that is being sent over the medium, or which is sent outside the chip, or sometimes it can be part of a system on chip. You know, nowadays you are familiar with the use of familiar with the system on chip. In a single chip, you can have a number of different subsystems. So, this can be one subsystem, 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 or it can be a multi-core. So, in such a case, you know, this particular subsystem, they may communicate with other subsystem, and you can have a common bus through which communication may be done. That means, these are all connected to the bus, and that is how communication can be done. This is one alternative. Another alternative, that you can put a switch through which they can be communicating. Whatever may be the case, whenever it is going from one subsystem going out to the another subsystem, again the same problem will arise, that means capacitance will be large. Now, whenever you are doing that, you can use two types of coding, as I was telling. One is your redundant coding, where m is greater than n. Another possibility is a non-redundant coding. In case of non-redundant coding, m is equal to n. That means, the number of bits that is being sent through the bus or through the switch, whatever it may be, or through the communication medium, can be same as the number of bits of the sender. So, in this case the number of bits is not increasing, that means there is no increase in redundancy, there is no redundancy. So, these are the two possibilities. Now, in addition to this categorization, another possibility is there, it can be you can have different type of mapping, say you can have 1-to-1 mapping, say let me do the categorization, say encoding techniques, So, you have two broad categories, number one is non-redundant, another is redundant. So, whenever it is non-redundant, obviously it will always be 1-to-1. What do you really mean by that? That means a particular code, n bit code, will always map to another m bit code. So, when m and n are same, we call it 1-to-1. That means a particular code here will map to another code here in a unique way. There is no possibility of one to many whenever you are having non-redundant coding, that means m is equal to n. Now, whenever you are having redundant coding, then you have two possibilities. One is your 1-to-1, another is your 1-to-many. So, whenever you are having redundant coding, then what you can have, a particular code can uniquely map to another code, or it may not map to another code uniquely, but it depending on the past history, the code to which it can map can be different. And as a consequence, 1-to-1 coding implementation does not require memory. You may say these are all memory less, neither in the encoder or in the decoder. So, 1-to-1 encoding does not require any memory for the implementation of the decoder or encoder. Now, you may have 1-to-many and there are two possibilities. 1-to-many can be static or 1-to-many can be dynamic. When 1-to-many is static, then encoder requires memory, encoder with M stands for memory, and decoder memoryless. Then we call it static. On the other hand, in case of dynamic encoding, both encoder and decoder will require memory with memory. So, we can see this is how we can categorize the encoding techniques into different types. So, we have non-redundant, then redundant, then 1-to-1, 1-to-many, that means one code will map to more than one codes depending on the past history, and in this case you will require memory as you can see either in the encoder or in case of both. Now, with this classification, we shall now move to different examples, different types of encoding that I have examples that I have already mentioned. First, we shall consider gray coding. Gray coding, you may be familiar with this. In gray coding, you may start with say you may say that this is, let us assume this is your binary code and this is your gray code. You may start with 1 bit, the binary value may be 0 or 1. So, whenever it is single bit, the gray code will also have single bit 0 1. So, in this case when it is 1 bit code, there is no change. Now, whenever we go to 2 bits, then you have got 4 possible alternatives, that means 0 0 0 1 1 0 and 1 1. So, these are the binary codes using 2 bits. what will be the gray code? In case of gray code, what you have to do, you have to take mirror image. That means, these bits will be 1 0 and the other bits will be same, most significant bits will be same. So, the code will be 0 0 1 0 0 1 1 1 1 0. That means, 0 0 will map to 0 0, 0 1 will map to 0 1, 1 0 will map to 1 1 and 1 1 will map to 1 0. Now, let us suppose we are interested in increasing another bit. So, you will be having 0 0 0 0, then you will simply repeat this 0 0 0 0 0 sorry 0 0, now it will be 1 1 0 0 1 0 1 1 1 0, then 1 1 1. That means, this part is repeated. Here what you have to do, instead of repeating, you have to make again mirror image. That means, it will be 1 0, it will be, then it will be 1 1, then it is 0 1, then it is 1 1. That means, here you have to add 0 and here you will be adding 1. This is how the mapping will be done corresponding to corresponding bits. So, you see what is the interesting property of this bit of these codes. You can see, any if you take any adjacent code, you will find their Hamming distance is only 1. That means, here this bit differs, here only 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 this bit differs. So, any two adjacent code will have Hamming distance of 1. So, you can extend this idea. That means, again if you want to have 4 bit, then it will be 1 1 1 1 0 1 1 1 1 sorry. So, 1 1 0 1, it was 0 0, sorry, we made a mistake here. So, 0 0 0 0, then it was 0 1 1 1 and so on. So, in this case you have to add another zeros here and it will be 1 1 1. Similarly, you will be adding 1 1 1 1 1 1 1 1 and of course, here it will be 1 0 0 0 1 0 0 1 1 0 1 0 and so on. So, this is how you can really realize Hamming code, but most, as I said, the most interesting property here, the adjacent codes are differing by 1 bit, and this can be used for the purpose of coding sending data. And as you can see here, it is very useful when the data is sequential and highly correlated, like instruction addresses. As you know, whenever you are writing a program is nothing but a sequence of instructions. How do you keep the instructions in the memory? You normally keep the instructions in the memory in adjacent memory locations, unless it is a branch, jump, subroutine call or interrupt. Normally, the instructions are kept in one after the other, I mean are in consecutive memory locations one after the other. That means, whenever you will be fetching instructions from the memory, in other words, when the CPU will fetch instructions from the memory for the purpose of execution on the address bus, they will come in consecutive order. So, in that case, instead of coding by using this binary code, if you code by using gray code, obviously the number of transitions will be much less, because as you go from this code to one code, only one transition, from this to this another one transition, from this to this another one transition, but this is not true whenever it is binary coded. As you can see here, it is from here to here it is 1 bit transition, but from to here it is 2 bit transition, from this to this it is 1 bit transition, but from this to this 1 2 3 bit transition. That means, the number of transitions can vary from 1 to 4 when it is a 4 bit code, but in case of gray code it is always 1 if it is consecutive. So, this is the crux of the matter for gray coding, and that means, it is useful when data is sequential and highly correlated. By highly correlated means, we are sending they are stored in consecutive memory locations. Obviously, the addresses will differ by fixed value, that means, depending on the size of the address bus, and as you know, memory is addressed by in terms of bytes, and as a consequence they will differ by say either 4 byte or 8 byte address, and that value will be fixed. And whenever you have that kind of correlation, then the number of transitions is limited to 1 for sequential data. However, when for random data the number of transitions for binary and gray codes are approximately equal. So, if the code, that means if the data is not correlated, that they are random in nature. So, in such a case you do not get this kind of benefit, that means the number of transitions of only 1 in case of gray code. So, this has been illustrated with the help of a simulation. I shall show about that. As you can see here, there is a comparison of the temporal activity. So, these are some of the here you have got a number of benchmark programs, first queens, quick sort, Q sort, reducer and so on. These are some benchmark programs which have been run on a processor, and as you can see on the instruction bus, when the addresses are coded in binary, then the number of bit transitions per instruction executed. Suppose a program requires 1000 instruction. So, and total number of transitions on the address bus is counted, and that is divided by the number of instructions to get the number of bit transitions per instruction, and that is being compared you can see in case of address bus. So, that is called instruction bus or address bus. So, you can see in case of binary coded form of the address, we find the number of bit transitions per instruction is 2.46, 2.64 and so on. On the other hand, when it is gray coded, it is reduced to 1.03, 1.33, almost half. So, there is a significant reduction in the number of transitions, and there will be consequent saving of dynamic power. And this has been taken from Chandrakarsan and Boderson's book on low power digital CMOS design, published by Clover academic publisher. However, this kind of advantage you do not get on the data bus, because data is not correlated. Data can be random, you can store some random values in your memory as data, and so there is no correlation in the data, and you can see the number of bit transitions per address per instruction is not reduced, sometimes rather it is increased. For example, for first queens, number of bit transitions per instruction is increasing slightly compared to binary coded data. So, you can see this particular approach, gray coding, can be used only when the data is highly correlated, as it is true in case of instruction bus, instruction fetching, or rather instruction address bus, where you fetch the instructions one after the other. Okay. Now, how do you really implement them? Implementation is rather easy. You can see here, you can code in a very simple way. I mean, you do not really require very complex hardware. You will require only n minus 1 2 to 1 exclusive OR gates for encoding, as well as n minus 1 exclusive OR gates for decoding. So, in both cases you require n minus 1 exclusive OR gates, and because Bn is Gn minus 1 is equal to Bn minus 1 and Gn minus 2 is equal to Bn minus 1 exclusive OR Bn minus 2 and so on. So, G0 is equal to B1 exclusive OR B0. This is how you can get the various gray codes, and similarly you can get back the binary codes in this way. Gn minus 1 is equal to Bn minus 1 and Bn minus 2 is equal to Gn minus 1 exclusive OR Gn minus 2 and so on. So, in this way you can get back the binary codes. So, from this you can make this conclusion that gray coding is a non-redundant code, because the number of bits is not changing. Here you have got n bits, here also you have got encoded code also has got n bits. So, the number of bits is same. So, it is a non-redundant code. Moreover, here you are doing one-to-one mapping, as you have seen, you have got a one-to-one correspondence between binary coding and gray coding. So, it is a one-to-one coding, one-to-one coding, and as a consequence you do not require any memory for the implementation of either the encoder or the decoder. So, as it is clear from this particular diagram, they can be implemented simply by combinational circuit, in this particular case exclusive OR gates. Okay. So, this is gray coding. Now, we shall consider another very interesting code, that is one hot coding. So, in this particular case, what you are doing, say you have got one particular device, maybe sender, then you are doing encoding, and here you have got decoder, and you have got your receiver. So, this is you can say this is your receiver. In this case, the n bit code that is coming from the sender is converted into 2 to the power n minus 1 bits on after the decoding. That means, decoder is converting to 0, 1, 1, in this way finally, it is 2 to the power n minus 1. So, you have got 2 to the power n minus 1 lines after decoding, and decoder, sorry, here it is encoder, this is decoder. So, decoder again we will convert it back to n bits. How it is working? Let us consider the basic idea behind this one hot encoding. Let us consider 4 bits, say 0 0 0 0, 0 0 0 1, 0 0 1 0. In this way you can have 1 1 1 1, 4 bits. This is the binary code. The one hot code will have 16 bits, 2 to the power 4 minus 1, that means the number of, it will be 2 to the power n, 0 to the power n minus 1. So, the number of codes is equal to number of lines will be equal to 2 to the power n, number of bits, not 2 to the power n minus 1. 0 to 2 to the power n minus 1, that is 2 to the power n. That means, in this case it will be 16. So, in the here it will be 0 0 0 0, 0 0 0 0, 0 0 0 0 and then 0 0 0 1. Because it is the 0 0 0 0, in this case the 0th bit is hot or 1. For 0 0 0 1, the corresponding code will be 0 0 0 1, 0 0 0 0, 0 0 0 0, 0 0 1 0. So, the next bit is hot or 1. So, in this way you can go on generating the code, and for 1 1 1 1 it will be 1 0 0 0, 0 0 0 0, 0 0 0 0 and 0 0 0 0. So, in this particular case, one important point that you have to notice is that only one bit is 1 and the Hamming distance between any pair of code is 2, always 2. So, that is the important characteristics of this one hot encoding, and as a consequence what is happening, two chips are connected using m is equal to 2 to the power n wires. So, you will require 2 to the power n wires, and an n bit data word is encoded by placing 1 on each of the ith wire, as we have already seen, and where 0 ith less than 2 to the power n minus 1 is the binary value corresponding to the ith bit pattern, and 0 is the remaining number of 1 wires, as we have already explained, illustrated with the help of this. That means, one of the bits will be 1 and remaining bits will be 0, and value will be here in this case it is 1, here it is 2, the next one will be 4, 8 and so on. Now, this guarantees precisely 1 0 to 1 and 1 1 to 0 bit transition when two different data word is sent. That means, whenever you are sending any pair. So, here you see if this was the earlier one, then if you are sending this 1 to 0 1 transition, 0 to 1 another transition. This is applicable to any pair of code. So, only 2 transition will all occur, number of transition is always 2. The number of wires required increases exponentially with the word size of the data. So, this is a very discouraging situation, because the number of wires, as you can see, is increasing exponentially. So, although this reduces the switching activity significantly, the number of wires increases exponentially as the number of bits increases. That means, it can be used for small values of n, not for large values of n. For n is equal to 8, the reduction in switching activity is 75%. So, you can see you can have 75% reduction in switching activity, but unfortunately, it requires 256 lines. So, n is equal to 8 and m is equal to 256. So, you see this is how the number of lines increases, and this is how you can implement one hot encoding. There is an encoder which generates 2 to the power n lines, and decoder converts it back to n lines. So, obviously, one hot encoding is redundant, and also it is a one-to-one encoding. So, this is an example of, I have already explained that one hot encoding, that redundant coding can also have one-to-one coding. So, this is the example of redundant coding with one-to-one mapping. That means, this one hot encoding is an example of this, and here you do not require any memory for its implementation, because it is a one-to-one coding. So, this is one hot encoding that we have discussed in detail. Now, let us consider another encoding which is very popular, bus inversion coding. So, in case of bus inversion coding, what is being done, the ith data word, let us assume it is SI, then you send either SI or SI bar, depending on which would result in fewer number of transitions. So, in this case, say S I minus 1 was the code that was, or the data bits that was sent. Now, you are getting SI. So, what you will do, you will compare the Hamming distance between these two codes. That means, this is the data bits, obviously, it will have n bits, this will also have n bits, and this n bit data is compared with n bit data, and Hamming distance is found out. And now, this was sent earlier over the bus, let us assume. Now, you have to send SI, and you have got now 2 choices. You may send either SI or you will send SI bar. When what you will do, you will find out the Hamming distance, between S I minus 1 and SI. So, if Hamming distance HD is greater than n by 2, that means, if the Hamming distance is greater than n by 2, what we will do? That means, if you send this, then if you send it, the number of bit transition will increase. That means, the Hamming distance is greater than n by 2. In that case, then send SI bar. On the other hand, if Hamming distance is less than or equal to n by 2, then send SI. Let me illustrate with the help of a very simple example. Let us consider you are sending 10110011. So, this is SI minus 1. Now, suppose you are let us consider an example where Hamming distance is greater than n by 2. Let us assume the next data Si is 1 0 1 0 0 1 1 0 0. So, in this case what is the Hamming distance? 1 2 3 4 5 and 6. So, Hamming distance is 6. That means, if you send this one, after this what will happen? Number of bit transitions on the bus will be 1 2 3 4 5 and 6. So, it is profitable, more profitable to send Si bar, and in the Si bar is 1 0 1 1 0 0 1 1. So, in such a case Hamming distance between this one and Si bar is, you can see it is only it is becoming same, no, 0 1 0 0. Unfortunately, I have taken the complement. Let me take up, let me make it 1. So, in this case 1 1 0 0 1 1 0 0. So, the Hamming distance is 1 2 3 4 5, 1 2 3 4 5. So, let us make it 1. So, 1 2 2 3 4 5 6. In this case it is 6, 1 2 3 4 5 and 6. So, in this case if you take the complement of it, it will be 0 1 0 1 1 1 0, then it is 1 0. So, now you compare the Hamming distance between these two, you will find 1 then 2 3. That means, if you send this, the number of transitions is 6. On the other hand, if you send this, why it is 3, it should be 2, 1 0 is 1 1 0 1 1. So, 1 1, so it will be 0 0. So, that means, here it is 2. So, we find that if you send Si bar, then the number of transition is becoming 2. So, it is profitable to send Si bar 2. That is how, by comparing the Hamming distance between the previous data and the present data, you can find out whether you have to send Si or Si bar. That is the basic idea of this bus inversion coding. So, it is a redundant scheme. Now, the question arises, how the other side will be knowing that inverted value of data has been sent, not the original data. So, you have to transmit one additional line to inform the receiver that the data that is being sent is inverted, and that is the reason why an additional bit known as polarity bit is needed, added with the data. So, this is the example, this is how it is being implemented. You have the sender and you have the encoder here, which converts the n bit data into n plus 1 bit, including this polarity bit. So, including this polarity bit, the number of bits is n plus 1. So, there is redundancy, but redundancy is not much, only one additional bit is added for transmission over the bus, and decoder will convert it to n bit. Now, in this particular case, how do you implement the encoder and decoder? In this case, decoder is memoryless, but encoder will require memory. Why encoder will require memory? The reason that encoder will require memory, because you can see when you are transmitting Si or Si bar, you have to preserve Si minus 1 and compare with Si. So, the code that you will be sending is dependent on the past history, what was sent earlier, and you have to compare with respect to that whether the Hamming distance is more or is increasing or decreasing, depend by sending Si, and accordingly you will be taking decision, and as a consequence the encoder will require memory. So, as it is mentioned here, encoder will require memory, however, your decoder will be memoryless. The reason for that is, in the decoding side, with the help of the polarity, you can easily know that you have to invert the data bits, or you have to take it as it is. So, that can be very easily found out from the parity bit. So, that the way it can be implemented is shown here. So, you can see this is the data that is coming, and you have the memory elements, as I have told, where you are preserving the previous value, which is being compared with the present data bits, and after comparing this Gx, which is computing the Hamming distance, or rather the polarity that has been sensed, depending on the Hamming distance, n is greater than n by 2 or less, it is finding out the value of p, and that p is being used to transmit the inverted data or the original data. And so, you are performing exclusive OR to decide whether you are complementing it or not. Similarly, the polarity bit is also sent through this memory element, and it goes to the other side. And you can see this is the decoder side, and the decoder side does not require any memory element, because it can simply implement it can be simply implemented with the help of n exclusive OR gates. So, here only one bit is shown. Obviously, if your data is n bit, you will require n exclusive OR gates to implement the decoder, and encoder will not only require n exclusive OR gates, n plus 1 flip flops, but some complex combinational circuit to compare the present data and the previous data that was sent over the bus, and find out the that whether the Hamming distance is greater than n by 2 or less. So, you can see encoder is with memory and decoder is without memory. So, this is the example of that. That means, I have already told, whenever you are having one to many, in this case it can map to one of the two values, complemented value or uncomplemented value, and accordingly encoder is with memory and decoder memoryless. This is the example of this particular situation, where you have got one to many encoding and using dynamic situation, static situation. Okay. So, this is your bus inversion coding. Now, we shall consider another very interesting example. Okay. Before I move to another example, there are some important features of bus inversion coding. The efficiency is dependent on the value of n, and efficiency is maximum, as you can see, the number of bit transitions by the number of bit transitions without encoding. That means, number of bit transitions with encoding by number of bit transition without encoding, that has been computed for different value of n. And here, as you can see, the this value is minimum, this ratio is minimum for n is equal to 2, and as the value of n increases, this particular value increases. To state in simple terms, you can see here, when the value of n is equal to 2, the switching activity reduction is 25%. So, this is 25% reduction is switching activity. So, it is 0.75. So, there is 25% reduction in switching activity. On the other hand, when n is equal to 32, so somewhere here we can see the switching activity reduction is only 11%, because here it is 89. So, it is 89. So, 11%. So, what does it really mean? That means, the whenever you are doing bus inversion coding, the efficiency is dependent on the number of bits, and it is maximum when n is equal to 2. That means, you get maximum reduction in switching activity, and you can have and as the number of bits increases, the efficiency degrades. In such a situation, you have got a trade off. What is the trade off? Suppose you are sending 32 bit. So, case 1, say you can send 32 bit including one parity bit p. So, in this case you will have a reduction of about 11% in switching activity. Now, you have got several alternatives. You group the bits into two parts. So, here you have got 16 and here you have got another 16, and obviously, you will require two polarity bits, says P 0 and P 1. Say it is D 0 to 15 and it is D 16 to 31. So, here you have got two additional polarity bits. So, you are increasing the redundancy by grouping into two types. So, in this way you can have third alternative, where you can group into 4 different components. So, here you have got D 0 to 7, P 0, then you can have D 8 to 15, then P 1, and in this way last one will be having D 24 to 31 and polarity P 3, P 0, P 1, P 2, P 3. So, and extreme case could be, say you can have only 2 bits, say D 0 1 one polarity bit, then D 2 3 another polarity bit. In this way you can have D 30 31, that means you have divided into 16 groups where you have got 15 polarity bits. So, here what is the trade off? Trade off is that you are increasing the redundancy, and as you increase the redundancy, obviously your area will increase of the chip, but the switching activity will reduce. So, here is a trade off between increase in area versus reduction in the switching activity. So, as you can see here, for n is equal to 2, switching activity is 20%, reduction is 20%. For n is equal to 32, switching activity reduction is 11%. So, here you will be having 25% reduction, and here you will be having 11%, and for these cases you will be having in between reductions. So, for large value of n, the n bit data bus can be divided into smaller groups, and each group is coded independently by associating polarity bit with each of the group. So, when a 32 bit bus is divided into 4 groups of 8 bits, it gives 18.3% reduction. That means, you get 18.3% reduction in this particular case, 25%, 18.3% and 11%. So, this is how the trade off changes. Okay. So, depending on your requirement, depending on the which one is more important, area is important or reduction in switching activity is important, you can choose one of the encoding technique. Okay. Coming to the last technique, that is your T0 encoding. In case of, we have already seen, in case of gray coding, the gray coding provides an asymptotic best performance of a single transition for each address generated when infinite streams of consecutive addresses are considered. That means, whenever you are running a program where the instructions are coming only from consecutive addresses and that number is infinite, in such a case the number of bit transitions asymptotically approaches to 1. That means, you do not have any jump, you do not have any subroutine call, you do not have any interrupt, but in reality that will not be so. Obviously, in reality the number of bit transitions will be little more than 1, depending on how many transitions occur. Say every 15 consecutive instructions there may be 1 transition. So, that in that case it will be little more than 1, but asymptotically it gives the value of 1. However, the code is optimum only in the class of irredundant codes, that is codes that employ exactly n bit patterns to encode a maximum of 2 to the power n words. Now, by adding some redundancy to the code, better performance can be achieved by adopting to T0. T0 stands for transition 0 encoding scheme, which requires a redundant line 1. So, here the idea is that you will be having some redundancy, but the number of transitions will asymptotically approach 0. How can it be done? And that is being achieved in T0 encoding. So, the T0 code provides zero transition property for infinite streams of consecutive addresses. How the encoding is done is explained here. Here you can see you have added a bit known as increment INC. But before I explain the encoding and decoding, let me explain the basic idea. Suppose initially the address was say 0000, and if you know the next address is 0000 and 0001, what you can do, instead of sending this one, you can send this one and inform the other side that you increment by 1. So, in such a case there is no change on the bus. Next time also suppose increases by 1 value, again you keep on sending this and inform the other side incremented by 1 from the previous value. So, this is the basic idea of this T0 encoding. How long you can continue with this? As long as it is only increment, as long as it increases by a fixed value known as S stride. If it is a 32 bit address, then the first 2 bits will be will that 32 bit means you will require 4, that means 2 bits. 2 bits will be required the 2 bit differences will be there between 2 adjacent addresses. Okay. So, I mean depending on the address size, it can be 2 bit, it can be 4 bit, because the address is usually byte encoded, it is specified in terms of bytes, address bus. So, this is the basic idea, and now you will be able to understand this encoding scheme. So, BT is the encoded transition which will be sending an INC, and you will be sending, and whenever BT is equal to BT minus 1 plus a stride, then what you will do, you will keep on sending the previous value and 1, indicating that increment bit 1, informing the receiver side that increase by 1. On the other hand, if BT is not equal to BT and BT minus 1, then of course, you have to send BT, a new value you have to send, and then increment bit will be 0. So, this is how the encoding is done, and other side again will do the decoding. If whenever increment bit is 1, then BT, it will be BT minus 1 plus S, that it has to be increased by the stride value, otherwise a new value will come, that is BT, and this is how it can be implemented. And you can see the encoder will be generating those BT bits and INC increment bit, and on the decoder side it will generate the BT. So, here it is capital BT and it is small BT, and this particular code is redundant in nature, but in this particular case you can see both the encoder and decoder will require memory. Why it will require memory? The encoder has to preserve what was sent, what is the next value, whether it will increase or it will change. So, previous value has to be stored. Similarly, the receiver also preserve the earlier value, because it has to keep on adding the new value S. I mean to get the new value, you have to keep on adding with S. So, that is the reason why both encoder and decoder will require memory. So, now we can conclude the bus encoding techniques. We have discussed basic concepts of bus encoding and considered 4 different encoding techniques: gray coding, one hot encoding, bus invert encoding, and T0 encoding. And these encoding techniques have potential to use in system on chip and multi-core architecture. Nowadays, lot of embedded systems are being designed, those are known as SoCs, system on chip, where you have scope for using this type of encoding. Similarly, multi-core is becoming increasingly popular, and the number of cores on a chip is increasing from 2 to 4 to 8 and so on, and there is prediction the number of cores may exceed to 56. So, in such a case also there is scope for large scale use of encoding within the chip. So, with this we have come to the end of today's lecture. Thank you.